So this lecture is on perfectly inelastic collisions. This is a section in your textbook 5.3. It kind of starts at page 235. It's not a full section in the book, but I treat it separately just because these I want to show you how to do these perfectly inelastic problems and the perfectly elastic problems a bit separately because they're a little bit more involved than just analyzing a collision. So you know that when we have a perfectly inelastic collision, we have two objects that kind of stick together. And a collision with these two vehicles that you see here is kind of an example. There's two initial velocities before, a VI1 and a VI2. And then afterwards there's just a VF, a final collision, a final velocity after that collision when the objects stick together. So please copy this down. This is the equation for perfectly inelastic collisions. And if you're wondering where this comes from, this is an analysis of the momentum of the objects. So we have, I won't go through how it's derived, but we have MAVAI plus MBVBI. That is the initial momentum. And we have our final momentum is MAB, essentially the mass of the two, times the VF, because we don't have an individual MA and an individual MB afterwards. If we isolate that conservation of momentum for VF, we're left with basically what we had on the left side of our equation for conservation of momentum for the initial state, divided by the sum of the masses in the final state when those two masses are combined together. So here's a problem we'll do. This is two objects. They collide together. One is 3 times as massive as the other. I think we saw this problem before, actually, but I'll switch to the camera and we'll work through this. So we have, with these two objects, let's write our VF equals MA, actually I'm going to call them M1, VI, or V1I, I suppose, plus M2, VI2, and divided by M1 plus M2. And in this problem, our M1 is 2.5, and that's going to be times 6. I'll take to the right as positive because that's how it's kind of treated in the way the question was displayed. M2 is 7.5, and VI2 is negative 15, and that's over 2.5 plus 7.5. So quickly calculating this, we get 2.5 times 6 minus 7.5 times 15. So this value here divided by what's essentially 10, because 2.5 plus 7.5 is 10. We end up with a VF of negative 9.75. In the question, we had 2 significant digits was our limit. So we're going to write this as VF equals negative 9.8 meters per second. I don't need to state the direction. In the question, it didn't say east, west, or up or down, or right or left. It used positive and negative, so we'll leave our answer as a negative. That tells us that the two objects will be moving to the left after the collision. This is a bit more of a complicated problem here. So I'll read through this whole thing, and then we'll work on this. It's a situation where we have a CSI investigator who shoots a bullet into a block, and he's trying to see how far this block would kind of displace in the vertical direction. So he's doing something about trying to see if a bullet in a situation that was seen at a crime scene kind of resembles something that would happen in reality. And what we'll do in this case here, we have our mass of our bullet is 5 grams, 5.5 grams. Write that down as its kilogram value. Our mass of our block is the 1.75 kilograms. Our initial velocity of the block is 0. Our initial velocity of the bullet is what we need to solve for. But we have the height displacement of the block afterwards is 0.125 meters. So this is this might confuse you a bit. It kind of looking at it, you might not be sure exactly what to do. These are our three givens. M lowercase b is the bullet, M uppercase b is the block. We're not going to use this equation first. In fact, we might not need to use it at all. So what we're going to do first is we're going to look at the kinetic energy, the situation where the kinetic energy would be conserved. So we have before the bullet is moving and the block is stationary. I'm not interested in the kinetic energy there because this is a perfectly inelastic collision. They stick together. The kinetic energy there is not going to be equivalent to the kinetic energy after. But at the point where the bullet enters the block, this is our bullet in the block, and it has not yet changed its height, so its delta H is 0 at this point. That's the time when I want to find my initial kinetic energy, or my EKI. I should write it down as EKI. And this is going to be, this kinetic energy is going to be similar, or actually it's going to be equal to the kinetic energy in this case. I'm sorry, not the kinetic energy, I shouldn't say that. It's going to be equal to the gravitational potential energy in this final case. So EKI is going to equal EGF because of the conservation of energy in that case there. There's no other force acting on them. There's no friction. There's no additional collision. So what I need to do now is I need to figure out this EKI is 1/2 of M of the bullet and the block, so MBB, and the VBB, which is my velocity that I need to solve for, is squared. And then on the other side I have MBB, G, and H. This MBB and this MBB will divide on both sides. I'm going to isolate for VBB, which is the square root of 2GH. Now this isn't the velocity I need to solve for, actually. I'm sorry, I did say that earlier. This is the velocity of the block and the bullet, the initial velocity of the block and the bullet. So this becomes the square root of 2. If you look at our givens in this question, we have 3 significant digits. We have 5.50 grams, 1.75 kilograms, and 12.5 centimeters. Because I have 3 significant digits, I'm going to use my 3 significant digit value for G, so 9.81. So when I calculate this, I will have 2 times 9.81 times 0.125, and I find the square root of that. I end up with a VBB of 1.566. Now, I'm going to use that 1.566 meters per second. That's not my solution yet, to find out what my initial velocity was of my bullet. So I'm going back to conservation of momentum, and my conservation of momentum is my mass of my bullet and my velocity of my bullet plus the mass of the block and the velocity of the block has to equal the mass of the block bullet times the velocity of the block and the bullet, which is known here. I know that my block was not moving initially, so I can scratch that out. And I need to solve for that VB. So my VB equals the mass of the block bullet divided by the mass of the bullet times the velocity of the block and the bullet. This becomes 1.7555 over my mass of my bullet, which is 0.0055, and my velocity, which is 1.566. I still have that in my calculator, so I'll start from that velocity, multiply that by 1.7555, and divide by 0.0055. I end up with a velocity of my bullet of 499.85, or 500 meters per second. So that is the 3 significant digit value. I already have it there. I don't need to write it, do anything else to show that it's 3 significant digits. In this case, it's just the final solution, but that would be your answer in 3 significant digits. Okay, we'll look at one more problem, and that's this one here. I like this problem because it actually involves going back to looking at our forces as well. So this goes to back to Unit 1 in this course. So we're looking at momentum, we're looking at energy, we're looking at kinematics, and we're looking at dynamics. So it's a nice question. So let's look at this here. We have a block that hits another block. They stick together, and they slide for a certain period of time. We need to find the friction that's acting on it. So our first situation, our strategy here is we're going to find out what is the velocity of these two when they combine together. So the first thing we need to find, and I'll just go straight to the page here. The first thing we need to find in this question is the VF, which is M. I think these were labeled as SB and LB. I'll just small block and large block. I'll just make it MS. So MS VS plus MB VB over MS plus MB. But in this case, our VB is 0, so this becomes the mass of the small block 0.500 times the velocity, which is 3.15, over 0.500 plus 3.50. This becomes, let's calculate this here, 0.5 times 3.15 divided by 4. I'm just going to write down all these values since it's a terminating decimal, and I'm in the middle of a problem. That's my velocity after. My momentum was conserved, so I've used conservation of momentum to solve that. My next thing I need to do in this problem is, now that I have this VF here is really my VI in the kinematics problem I need. So 0.39375 meters per second is my VI. My distance traveled in this problem is the 2.63 centimeters. And my final velocity, because I'm going to stop here in this problem, is 0 meters per second. And I need to find the A. So we can go back to our equations of motion. Go over here and solve this. And using our equations of motion, we're looking for an equation that has VI, D, VF, and A. So the one that doesn't include time, which is VF squared equals VI squared plus 2AD. And I'm going to isolate that for A. My VF is 0, of course, because I'm stopping this block. So this becomes A equals negative VI squared over 2D. So my A is negative 0.39375 squared over 2 and times 0.0263. So let's figure this out. So this value, which I still have my calculator, squared divided by 2 divided by 0.0263. I end up with an acceleration of negative 2.9475 meters per second squared. So I know it's going to be negative because it's a frictional force that's causing this. Now I'm going to go to my F equals MA and just isolate. Sorry, for F is already isolated for. I don't have to do anything else there. F equals my mass of the two blocks together. So that's going to be 0.500 plus 3.50 times my A, which is negative 2.9475. So this value here, multiply this by 4, I end up with a force of 11.79. That's negative. And when I round for significant digits, I'll rate it as a positive because I know it's a frictional force, so it's going to be opposing. But it's going to be 11.8 newtons. Because if we look back at this problem, actually, no, I'm sorry. I misunderstood. There's a difference between the question picture and the question that in words there. One value is given as 0.500 in the picture. So let me just show you here. The other value, so one is 0.50 kilograms, and when you read the question, in the picture it's 0.500. So I guess your answer should be reported in 12 newtons if you're taking your information from the question, and it's going to be reported as 11.8 newtons if you're going to report it from, take the values reported in the picture. I will not make a mistake like that on a test, so don't worry about that, but please make sure you're following the significant digit rules as you do all of the tests and quizzes in this course.